One important reaction of conjugated dienes is the Diels-Alder reaction, which will be the focus of this video. The Diels-Alder reaction is one of the important named reactions in organic chemistry, where the reaction takes on the name of its inventor. It's one of the most straightforward ways to make a unsaturated six-membered ring from all acyclic starting materials with control of stereochemistry. The simplest example of the Diels-Alder reaction is shown here with 1,3-butadiene and ethylene. The Diels-Alder reaction always involves a conjugated diene, which normally of the two partners is the most electron rich, so we can call that the nucleophile. The other partner is referred to as the dienophile, and normally it's electron deficient, and it could either be an alkene or an alkyne. In this case, it's an alkene. When you heat these two reactants, a concerted reaction will occur in which the 3 pi bonds are used to make 2 sigma bonds and a new pi bond. This is referred to as a 4+2 cycloaddition reaction, the 4 and the 2 referring to the number of pi electrons participating from the diene and the dienophile. In this process, overall, we have 3 pi bonds being converted to 2 sigma bonds and 1 pi bond in the new cyclohexene product, which is one of the driving forces of the reaction because sigma bonds are more stable than pi bonds. The reaction also occurs with an alkyne as the dienophile, and in this case you still have 2 new sigma bonds and a pi bond formed, but the product will have a 6-membered ring with 2 double bonds. Some examples of the Diels-Alder reaction are shown here. Notice that we have a diene, 1,3-diene, a conjugated diene involved in every example. We also have dienophiles. Notice that the dienophiles have substituents on them, and normally they're going to be electron withdrawing groups. In each case, we have 3 pi bonds being consumed to make 2 new sigma bonds and a pi bond. Using these examples above, see if you can write out the Diels-Alder reaction products for the 2 reactions shown below. As usual, you should stop the video and see if you can provide the answers before they're displayed on the screen. Starting with the one on the left, the first thing you have to do is identify the diene. Here it is. And the dienophile, which would be this alkene that's conjugated to the 2 carbonyls. Much in the same way that's shown above with these arrows, you can indicate the concerted reaction. In this case, with these arrows, that it doesn't matter which direction you go or where you start. You're basically just saying that 2 of these pi bonds are going to be used to make a sigma bond, and one of these 2 pairs of electrons is going to form the new pi bond in the 6-membered ring. And highlighted here is are the 2 new sigma bonds and the pi bond in the newly formed 6-membered ring. In this example on the right, we have once again a conjugated diene, but we have an alkyne, a conjugated alkyne, and this alkyne will react in the Diels-Alder reaction in the same way that the alkene dienophile did, providing 1 pi bond, and you end up now with a 6-membered ring that has 2 double bonds on opposite sides of the ring. There are some rules and restrictions associated with the Diels-Alder reaction. First, the diene must be able to adopt the so-called S-cis conformation, where S stands for sigma bond. The term cis and trans, normally we use to describe the relative position of substituents on a double bond or on a ring. In this case here, we're using it to basically point out the position of the two double bonds of the diene relative to each other. So in this case here, they're pointing in opposite directions along this carbon-carbon sigma bond, and so we say that they're trans to each other, and this would be the S-trans conformation. It has to be able to rotate around this sigma bond. In this case here it does because there's nothing hindering it, but you could imagine that if you place certain substituents on this double bond here, on either of these double bonds, you could restrict rotation to prevent this switch from S-cis to S-trans occurring. But in this case here, it's free rotation, and you end up with the S-cis conformation that's required for orbital overlap to achieve the Diels-Alder reaction. Another restriction would be that the dienophile should be connected to what's called a strong electron withdrawing group, so that it makes the dienophile more electrophilic and allows it to be more reactive to react with the nucleophilic diene. What is meant by a strong electron withdrawing group? Well, it can usually be defined as a polar functional group that has a multiple bond that's conjugated with the double bond of the diene, and it can withdraw electron density by a resonance effect. So when you look at this example that's shown here, we can consider this to be a strong electron withdrawing group. It has a carbonyl, a C double bond O, with a pi bond, so all of these are sp2 hybridized, and therefore the electrons in this system are conjugated. Oxygen's more electronegative than carbon, so you can imagine that these electrons are all being pulled toward oxygen, making this double bond electron poor. This can be more clearly demonstrated by drawing what are called charge-separated resonance structures, that is, charge-separated Lewis structures. These are bad Lewis structures, and you can see why, because certain atoms don't have octets. They're bad Lewis structures, but this is generally a good method to gauge chemical reactivity of molecules that have polar conjugated systems. And we're going to refer to these charge-separated resonance structures, the use of charge-separated resonance structures throughout the course. In a charge-separated resonance structure, you're basically looking at a polar bond, and you are bringing it to the extreme. We know that oxygen's more electronegative than carbon, so we'll just give these two electrons in the pi bond to oxygen, and we generate a Lewis structure that looks like this. Again, it's a bad Lewis structure, but it reveals the electron poor nature, the electrophilic nature of a carbonyl. And you'll see that there are chapters devoted in your textbook to reactions in which a nucleophile attacks this carbon. So this charge-separated resonance structure reveals that this carbon's electron poor. We can continue to draw another charge-separated bad Lewis structure, and in this one you can actually see that the double bond is no longer present in these two carbons. So by drawing these charge-separated resonance structures, you reveal that this carbon-carbon double bond is electron poor because of the electronegative nature of this carbonyl, which is pulling electron density out of the ring. And this is just a way to manifest it, to show it on paper, how this is occurring. This, no doubt, is the best Lewis structure for this molecule, but remember that these are bad Lewis structures, and this is just a gimmick or technique in order to gauge the reactivity of polar conjugated systems. Another rule of the Diels-Alder reaction is that the stereochemistry of the dienophile is retained in the six-membered ring cyclohexene product. When we're talking about the stereochemistry of the dienophile, which is a double bond, we're talking about whether the substituents are cis or trans to each other on the double bond of the dienophile. The example that's shown here is one 3-butadiene reacting with a dienophile which has substituents which are trans to each other. The reaction is concerted, which means bond making and bond breaking occur simultaneously, which means that there is no rotation around this bond, the bond between atoms 5 and 6. So if it's syn addition and the diene approaches one face of the dienophile in this transition state, remember this is a concerted reaction, so there are no mechanistic intermediates, but there is a transition state. In the transition state, we're forming a new sigma bond between atoms 1 and 6, and a new sigma bond between atoms 4 and 5, and a new pi bond between atoms 2 and 3. If I follow through on this transition state, I end up with a structure that looks like this. So you can see the two new sigma bonds and the new pi bond. Notice that, again, this is trans-stereochemistry in the dienophile. If it's a concerted reaction and there's no rotation around the bond between atoms 5 and 6, in the final 6-membered ring product, the two substituents, these two ester groups, which were trans in the dienophile, are going to be trans in the 6-membered ring product. This is a rather tortured looking drawing. It just follows through from the drawings of the transition state. But we can just take this and draw it in the way that we normally do for a 6-membered ring, is that all of the atoms in the 6-membered ring are in the plane of the paper. And then the substituents on the ring their stereochemistry is indicated by wedged and hashed bonds. So you can more clearly see here that the stereochemistry, the trans stereochemistry of the dienophile was carried through in the 6-membered ring product, where the two ester groups are trans to each other on the newly formed ring. When the Diels-Alder reaction occurs with a cyclic diene, the product is a bridged bicyclic compound. Here is an example of a bridged bicyclic compound in the box at the left. You see that there are two 5-membered rings which are sharing two non-adjacent atoms. You can think of it as this atom at this bridgehead and this atom at this bridgehead are connected by a 1-carbon bridge here and a 2-carbon bridge over here and another 2-carbon bridge over here. So this is why they call this a bridged bicyclic compound. In the example above, we have 1,3-cyclopentadiene as the diene, and the dienophile is ethylene. When you heat this up, you form two new sigma bonds, shown here in red, between atoms 1 and 6 and 4 and 7, and a new pi bond between 2 and 3. This is a top view of the bridged bicyclic compound that is afforded. This is a side view, and I think it's a good time to take out your molecular models and make a model of this so you can actually see how these drawings are representing the true three-dimensional structure of the bridged bicyclic compound. When the cyclic diene reacts with a dienophile that has a substituent on it, there are two possible isomers of products, stereoisomers, that could be afforded, depending on how the diene approaches the dienophile. The two products are shown here. You have the so-called endo product, where this group Z, which was on the dienophile, is pointing down when you draw the bridged bicyclic compound in this fashion. That's called the endo product. When it's pointing kind of in an equatorial position, so you can consider this to be sort of axial, this to be sort of equatorial, this is called the exo product. And another rule in the Diels-Alder reaction is the rule of endo addition. When endo and exo products are possible, it's the endo product which is preferred. So you can consider the endo product to be the kinetic product in this reversible reaction. All right, how can we explain the formation of endo and exo isomers in the Diels-Alder reaction of dienophiles with cyclic dienes? Well, depends on the way that the dienophile approaches the diene. If it approaches the diene with the Z group sort of tucked underneath facing the diene, In the transition state, you can see you're forming a six-membered ring. Here are the two new sigma bonds and the new pi bond. If we just take this structure and prettify it a little bit, just by tilting it up and making it look a little bit more presentable, you can see that this is the endo product. So by having this Z group tucked underneath, you get the endo product, where this Z group is kind of pseudo-axial. The other way that the dienophile could approach the diene is by having the Z group pointing away from the diene. In the transition state, you can see again the six-membered ring forming, the two new sigma bonds, the new pi bond. Just take this, straighten it up a little bit, and you can see that this is the exo product, where the Z group in the newly formed bridge bicyclic product is pointing in a pseudo-equatorial position. So when the Z group is facing away from the double bond, the diene, you end up with the exo product. So remember that the rule of endo addition says that when there's a choice between these two, it's the endo product which is formed first. It's the major product in the reaction. As I said, you can consider it to be the kinetic product. So there's something that is favoring the Z group being tucked underneath the diene. And there's something called secondary orbital effects, which are a kind of a bonding effect between orbitals on the Z group. Don't forget the Z group is normally, could be a carbonyl, or it could be some other unsaturated group that has pi electrons. So there's a favorable bonding effect that's allowing this transition state to be lower in energy than this transition state. And so that's why this is the product that forms fastest, the kinetic product. So the rule of endo addition says that if you have a choice between the formation of the endo or the exo product, the major product, the one that forms first, is going to be the endo product. Even though the Diels-Alder reaction is a very old reaction, it's still a very important reaction used in the synthesis of molecules of biological importance. The example I'm showing you here is going to be the synthesis of a molecule called Tamiflu, and it is a drug that was used frequently during the H1N1 flu pandemic back around 2009. And it was normally prepared by structural elaboration of a molecule, a natural material that was obtained from star anise. So this is a natural material. It's something that you may have even seen in the grocery store. But the problem was that they had to crank out so much of this Tamiflu that they had very limited supplies of the star anise, and that was the bottleneck. That was preventing large amounts of this from being synthesized. So at the time, chemists decided to come up with different synthetic routes to make Tamiflu. And one route that and here's a here I'm going to point out the six-membered ring with the double bond. So notice that this is a prime structural feature for the synthesis in the Diels-Alder reaction. E.J. Corey from Harvard published a synthesis where the very first step in the synthesis was the formation of the six-membered ring with a double bond, and then he continued in a number of other steps to make this material here. So I just wanted to show you this as an example of the utility of the Diels-Alder reaction in chemical synthesis, particularly for making molecules of biological interest. If you have a synthetic target that you think might be able to be synthesized via the Diels-Alder reaction, the first thing you should do is identify the six-membered ring with the double bond in the molecule. So that is absolutely necessary if you want to actually synthesize something via the Diels-Alder reaction, because that's the product of the Diels-Alder reaction. Once you've identified it, then what you can do in a retrosynthetic sense is sort of do a reverse Diels-Alder reaction, use the same aeroflow that you did before, and you're basically sort of disassembling this six-membered ring into its component diene and dienophile. And you can see that you can do the same thing with these bridge bicyclic systems here. We have two problems at the bottom of the page. See if you can figure out what diene and dienophile are required to synthesize this compound and to synthesize this compound. Again, you should stop the video and see if you can work out the solutions before they're displayed here. All right, so for this one, number one, identify the six-membered ring with the double bond in it. And there it is. So we have a cyclohexene right here. At this point, we can do movement of arrows in the reverse direction. And we should end up with a dienophile that looks like this, and the diene being 1,3-butadiene. Moving to the next one, again, first identify the six-membered ring with the double bond. That's right here. Then in again, in the same fashion that you would move electrons when writing out the forward Diels-Alder reaction, just do it in a retro sense and disassemble the six-membered ring into its diene and dienophile components. In this case, we end up with this conjugated diene and this as the dienophile. You should attempt to provide syntheses of these two compounds, and each synthesis will involve chemistry of conjugated dienes.